We're going to do a lesson on logarithmic differentiation. This is our last technique we're going to learn to do derivatives. Okay, this is part of D2 and D3. Now, how will you recognize logarithmic differentiation when you're looking at it on a test or when you're working? Is you'll notice that there's a lot of functions that look like a lot of product rule, quotient rule. So this would be product rule. There's chain rule inside mixed with quotient rule and chain rule. And so we want to make sure that we have a technique to help us solve these derivatives that are complicated. Now, in an example like this, it is not necessary to use logarithmic differentiation, but it will actually make our work a lot easier. So what logarithmic differentiation does is we start taking the log or the natural log of both sides as a tool to help us simplify the original function to make the derivative easier to work with. So I take the log of both sides, or the natural log of both sides, and now I'm going to use the log properties to just simplify. So all I'm doing at this moment is simplifying the function. So I can break it up using the log rules. If I have two things inside the log that are being multiplied, it changes to the sum of the two logs individually. When I have a division, I use a subtract to the power of 5. My exponents can come down. So 3/4 ln x plus 1/2 ln x squared plus 1 minus 5 ln 3x plus 2. Now when we look at this point, we haven't actually done anything other than simplify the function and write it in a different way. Now we're ready to differentiate. So let's take a derivative, but now we have to do it implicitly because y is not written as a function of x. So the derivative of ln of y is 1 over y times the derivative of y, which is y prime. The derivative of 3 over 4 ln x will be, well, here's my constant. The derivative of ln x is 1 over x. Constant multiple stays on the outside. The derivative of x ln of x squared plus 1 is 1 over x squared plus 1 times the derivative of the inside, which is 2x, minus constant multiple leaves the 5 on the outside. The derivative of ln of the argument is 1 over the argument, derivative of the inside because of chain rule. Now remember, our goal is to solve for the derivative, so I need to isolate for the derivative. So I'm going to multiply both sides by y. So y times all the stuff that was here. Now I'm going to clean it up as I'm writing it. 3 over 4x plus x over x squared plus 1. You're going to notice that the 2's cancel out. Minus 15 over 3x plus 2. So now the only thing is I have an expression for y, so I want to come back and sub that in, and then I've solved the derivative without having to actually use complicated product and quotient rule mixed with chain rule in this big ugly expression. Now in this question, the logarithmic differentiation was not mandatory to do. It was there to help us to make the derivative actually simpler to solve. But in other examples, it may actually become necessary to do logarithmic differentiation as the technique to solve the derivative, because that's the only method we have to solve the derivative. So when we get to the next example, you'll notice so basically, before we get to that next example, when you're doing logarithmic differentiation, we're taking the natural log of both sides, and then we're using that to simplify the function. Once we're done simplifying the function, we're going to differentiate implicitly. So again, every time we have a y term, we have to differentiate by having a y prime term, and then we isolate for y prime, which is the derivative of the function. Okay. The derivative of a constant is 0, we know that. The derivative of a power mixed with chain rule is you do the outside first, so b, bring it down, leave the function the same, reduce the exponent by 1, take the derivative of the inside, which is f prime of x. The derivative of a base to the power of a function of x, you leave it the same, ln of the base, derivative of the exponent, which was what we found in yesterday's lesson. Okay, so now basically when we want to do logarithmic differentiation on a function where there's a variable in the base and a variable in the exponent, we have no choice but to do logarithmic differentiation. It's not an optional tool, it's a mandatory tool to use. Must use this. Okay, so let's look at an example. We're going to recognize that we have to do it. We're going to notice that there's an x in the base and there's an x in the exponent of some sort. So let's go through and differentiate. In order to do this, we need to do logarithmic differentiation, which means take the ln of both sides, or log, natural log of both sides. Now, what we do is before I take the derivative, I want to clean up the function to what I want it to look like before I differentiate. Exponents are allowed to be pulled down. You have to watch your log rules. Log a over b is log a minus log b. This is all 30-1 rules. Log a times b is log a plus log b. If I have log a and it's raised to some exponent c, that c can come out front. So now I'm ready to differentiate. The derivative of ln y is 1 over y prime. That's implicit and chain rule. This becomes product rule. I have two functions. The derivative of the first, 1/2 x to the minus 1/2 times the second plus, leave the first one the same. The derivative of the second one is 1 over x. So I'm going to clean this function up a little bit, move the y to the other side by multiplying. 1, so this is going to become ln x times 1. The x to the minus 1/2 will move to the denominator as a radical, plus a radical x and an x mean that simplifies to, I can subtract the exponents, and I'm going to get an extra radical on the bottom. So x to the 1/2 divided by x to the 1. I can subtract the exponents and get x to the minus 1/2. Now I could do more work and further simplify this expression, but you would have to just look at a question and see what level they want you to get to. I mean, we could write this function as ln x plus 2, making a common denominator and writing it all as one fraction. So that's logarithmic differentiation. Now there are some examples here for you to try. For your benefit, I might just try, like, say, number 8 for you, just as practice. Now with this one, this is just your regular techniques. We're just ready to differentiate this function. Actually, as I look at these ones, none of these techniques actually require you to do logarithmic differentiation. The only ones that would require us to do logarithmic are the ones with variable in the base and variable in the exponent. So again, none of these ones actually require it. So you can use whatever techniques you're used to. Let's just do number 8 because I said I was going to do number 8. So the derivative of x, we have to remember the derivative rule for log x. So log base b of x is 1 over x ln b. So this will be 1 over the argument x e to the x ln of the base. But now because there's chain rule, I need to do the derivative of the inside, which is product rule. Derivative of the first times the second, leave the first the same. Derivative of e to the x is e to the x. And that would be my derivative of that function. And that's logarithmic differentiation. Pretty much you have to recognize where it is mandatory to use. This one again, logarithmic is mandatory. Okay, and in this example, logarithmic was optional but helpful. Logarithmic, helpful, but optional. Okay, again, really recognize it by looking for the form where there's variable in the base, variable in the exponent. That's the key to the lesson today.